How do I get this one?
Okay, so our third and final for today presentation is another NASA Center internship talk. Alessio, it's close to you. Okay. Should I bear it? Sure.
All right. Okay, hi everyone. My name is Alessio. I'm a graduate research assistant here at the University of Minnesota, and I work on a project called IQ. And in particular, I'm in charge of incorporating an emission spectrometer in the payload. Got quite a few people working on this, so let's dive in. This works. All right. So HiCube, which stands for Hypersonic Configurable Unit Ballistic Experiment, is a CubeSat that will re-enter the atmosphere at hypersonic speeds. And it aims to collect aerothermodynamic data during descent in order to validate and improve existing models in hypersonics, so computational models. Like I said, one of these key components will be an emission spectrometer. And the point of including this instrument is so that we can characterize the chemical species in the flow behind the post-shock. So like I said, this is a multidisciplinary project. And one of the goals that HiCube has is to prove that we can collect this kind of data with a low-cost, low-risk, repeatable experiment. We are leveraging a formal Space Act agreement between the University of Minnesota Twin Cities and NASA Ames Research Center with the TechEdSat team. So basically, we are the passenger and they are the bus. They will provide the ride and we provide the payload. So today I'll talk about some preliminary design choices that we've made. Then I'll move on to talk about some design choices that we're making right now by using some US3D simulations and a software that NASA provides. It's called NECAIR. I'll talk a little bit about my experience at the NASA Center, and then we can go on for some questions. So we had to make some choices regarding the physical shape of HiCube to begin with. And in order to do this, we informed these decisions by using US3D simulations, which are provided by the University of Minnesota Hypersonics group with Graham Candler. As you can see from the figure, we have two different body styles. One of them is a hemispherical model, and the other one is a little bit more blunt. So the radius of curvature on each of these is shown, and you can see the maximum temperature in the flow. So that's not necessarily on the vehicle body, but it is in the flow. So key takeaways from this is that we have extremely elevated temperatures in the flow, and that we have steep gradients as the flow moves past the forebody.
So Alessio, remember the people on Zoom don't see the laser shot.
Okay.
The left-hand figure, the right-hand figure.
Okay, that's a good point. Thanks. So like I said, we have some high temperatures and steep gradients. So one of the things that we were kind of considering is, do we want a hemispherical model or a blunt one? We ended up going with the blunt model just because that blunt configuration, it moves the shock away from the physical body. And so the temperature on the surface is slightly mitigated, not by a lot, but enough to make it the choice that we want to make, essentially. And that's constrained by thermal protection system limitations. So as the vehicle gets hotter, we want to ensure that the thermal protection system can protect what's inside the spacecraft. And the blunt configuration is going to allow us to do that. So like we've seen these high temperatures, clearly in excess of 1800 degrees Kelvin. And in this kind of flow, molecular species in air, so we've got in just standard air, we've got about 78% oxygen and 20%, 78% nitrogen and 20% oxygen. These begin to dissociate, react, and ionize. And they form nitric oxide, which is one of the prevalent emitters in this kind of flow. And that's formed by the Zeldovich reactions. As you can see, N2 is reacting with dissociated oxygen, and O2 is reacting with dissociated nitrogen. So because NO is one of the prevalent emitters, we've seen that it emits in the ultraviolet region of the electromagnetic spectrum. And so we've chosen a spectrometer, a compact one from Ocean Insight. It's called the Flame S UV-Vis. From that name, you can probably infer that it fields, UV and visible wavelengths in the electromagnetic spectrum. So, in order to study the chemistry behind the flow, we have to have line of sight data. And the US 3D simulations provide that in addition to all the physical properties of the flow. So we've got an 11 species model, which is predominantly N2O2, nitric oxide, and their ionized counterparts, and we also have free electrons in the flow. Once we extract this line of sight, we're going to input that into NASA NECAIR, which, as you can see, is non-equilibrium radiative transport and spectra program. So in the right side, that figure shows some of the line of sights that we are considering. On the forebody, we have a 5-degree angle. We call that the viewing angle for the line of sight, 15. And then we have two different 45 degrees. There's one on the corner and one at the shoulder. The corner one is not necessarily feasible just because you have that corner, and putting a window on the corner is quite difficult. But we wanted to compare it to the 45 degree on the shoulder, where it would be possible to insert a sapphire window. And then, of course, there's also a 90-degree angle. So what we'll do is basically compare spectra for various configurations. So we've done it for the hemispherical model, and we've also done it for the blunt one. But for the sake of this presentation, I'll be talking about the blunt model. And for each one of these configurations, we also have these multiple angles of viewing to the line of sight. So we already heard that these chemical species are reacting and ionizing. They're absorbing a lot of energy, which makes kind of moves them, it excites them into higher energy levels. And as they move past the front of the flow, they start to cool down and they start to relax, and they lose energy, returning to lower energy states. They lose energy in the form of radiation. So NECAIR is a line-by-line program that computes emission and absorption due to transitions between these various energy levels, and it emits the emission spectrum. So it's basically showing us what wavelengths these radiations are happening at. So on the right side, the top plot has an entire spectrum. So that goes from 0 nanometer wavelength all the way to 1,000. That's basically the entire output that NECAIR shows. In the vacuum UV, we have that high spike. We can't see that with our spectrometer, so we automatically going to discard that part of the spectrum. But mostly that is just the unreacted species of air. And towards the right of the plot, there's gray body emission. We can't really tell any information in here just because all these wavelengths are blending together, so we can't really see any detail within the chemical composition. However, we can get some good detail in the ultraviolet region, which is excellent for us because that's essentially what we're going to be looking at with the flame spectrometer. You can see those wavelengths, and so we don't need to worry about the gray body, but we can see UV, where NO is one of these primary emitters. You'll see some other spikes there. Those are ionized oxygen and nitrogen as well. So these simulated spectra are going to help us inform another design choice. So once we've chosen the blunt body, now we have to choose where do we want to point the spectrometer, and where can we build a sapphire window onto this forebody so that we can collect this data. So I have two plots on here. The left one is showing the comparison between two of the lines of sight on the forebody, and then the 45-degree angle that you saw on the corner. What we can see from these two is that as we increase the angle for the line of sight, we're losing intensity of signal, but we are not losing any structure. So the individual peaks and bands that you see on these plots, they continue to be there as we change the viewing angle. But we're not losing any information, we're just losing the amount of signal that we're getting. Which could be a challenge depending on how sensitive the flame spectrometer is. And one of the variables that we can control in order to allow more light in is the integration time. So that is something we're investigating right now. We're doing tests on the spectrometer to see what its sensitivity is, if it can read these kinds of intensities of light, and how we can adjust the integration time to allow enough light in to see what we want to see. As far as we can tell, it's going to be easier to build a window on the side, so at that shoulder. But you can see that that 90-degree view has a really, really weak signal. The 45-degree view at that shoulder is a little bit better. But if we were able to somehow find a way to put this window on the front of the body, that's where we would see the most intensity. It would be easier to collect this data. So during my time at NASA Ames Research Center, with the other two interns that were there with me, we essentially worked on the mechanical integration of the flame spectrometer into one of these TechEdSat buses. So in the bottom right, that's a 3D CAD model of TechEdSat 12, which is the first flight that will fly one of these spectrometers. The first thing we did was some functional testing to see how the instrument worked. We tried the data acquisition, see what format it was output in, and how we could start to visualize that data as well. Another thing that we did with the spectrometer, against the company's best advice, was we opened it. And we wanted to see what was inside and if it was rated for space. So like if anything in here would outgas and compromise the integrity of the instrument, because the inside, you can see at the bottom left there, there's a couple mirrors and there's a diffraction grating and a crystal. If any of that gets damaged or polluted, that ruins your spectrum. You're not seeing anything anymore. So we found that everything in the spectrometer looks good. It can be used in space. The only thing is there are 6 screws. So in that next one, from the right of the bottom left, there's 6 small screws on that printed circuit board, and those need to be staked so that they do not loose. Everything else can be used in space. So it's a really good sign. Next, I can talk about the working payload emulator that we built, essentially. So you can see the flame spectrometer. This is in the top right. This is the flat sat that we built. We have the flame spectrometer. It's connected through a DT4 connector. It is a 40-pin connector. It has various GPIO inputs, so general input output. And it also has the hardware and firmware for serial RS-32. So that is what we ended up choosing because that's the only way the spectrometer acted as a slave instead of a controlling device. We wanted to keep the flight computer the controlling device. So we chose RS-232. We have 2 converters that go between the spectrometer and the flight computer. Right now, in that image, there's just a stand-in microcontroller. But TechEdSat's flight computer is an Arduino Portenta, which will be able to communicate with the plane. And then in the top right of that same image is the Iridium modem. That is going to be one of the ways that we will communicate the data back down to Earth. So TechEdSat 12 has a lunar radio, and we will also be using the Iridium constellation to get down this information. And then, like I said, you have plans for mechanical integration. In the bottom left, that CAD model, the red box is the spectrometer. So it's just going to be looking out the side for now. We just want to send it up into space and see if it works. If we can communicate with it and if we can get a spectrum down. So that is essentially everything that we did in our time at NASA Ames. Now I can talk a little bit about the rest of the experience. So it was really fun to be on the NASA Center campus. It was a warm, welcoming atmosphere. I think everybody there was generally happy to see people on the campus. After COVID, it was kind of deserted. So when they saw all of us there, they were really excited to have people there to work with. They provided us with lots of tours of different facilities on campus and off campus. So we got to see, on campus, we got to see all the wind tunnels. So in the bottom left, there's the test section of the 80 by 120 wind tunnel, which has what they call the biggest open window in the world. And that is the inlet to the left of that image. And then in the bottom right, that is Hangar 1, currently stripped. They are working on getting it covered again. Outside of the NASA Center, they brought us to other places like Stanford Dish. And they brought us to other campuses like Apple, Google. We got to see a bunch of different things in the area. So that was one of the things that I really liked, is they essentially told us, we want to see how you like the area and how you fit in the center. So they really cared about us having a healthy work-life balance while we were there, so that we could enjoy our surroundings and also enjoy our work there and see if we fit in at the NASA Center, and that might be something we're interested in pursuing. Some advice that I have is get out of this internship what you put in. So talk to your mentors, ask questions, be interested, ask to be challenged, and that's the best way to learn new skills, because odds are they always have something for you to do. And again, those mentors are there to provide help and insight, so ask as many questions as you can. They're really friendly, and like I said, it's a great experience. I would recommend it for anyone. So now I have some time for some questions.
Historical question, what is Hangar 1?
Hangar 1 is one of the largest freestanding structures in the world. It is...
and why did they have such a big hangar?
I think it was for Sophia. I don't remember.
It's for the airships.
The airships, that's right. And so we didn't get to tour Hangar 1 because it was stripped, but we got to tour the other two hangars, and there was quite a few airships in there. They just can be in there without hitting the ceiling, which is kind of weird. Okay. Sure.
It looked like that satellite you had on there was a 12U. What are you guys going after?
So that one's actually a 6U.
It's a 6U?
Yes.
Okay.
So it's 2x3. All our flights will be in a few different configurations. So this first one is going to be a 6U. Some more flights will be a 3U, so 3x1, and one of the other flights will be a 6U, but it's 6x1, so a little bit longer. So there'll be different configurations. Yeah.
So you have to choose just one window, right?
Yes.
How does the light get into the spectrometer? Is it through an optical cable?
Yes. So the spectrometer it has a fiber optic cable that will go essentially through the body and into the thermal protection system, and the optical element will be placed right behind the sapphire window.
Would there be a possibility to have multiple windows and move the cable? Look out this way, look out this way, look out this way.
Probably not on one of these experiments, because that would require some complexity to the spacecraft. And as we've learned, adding moving parts into a spacecraft adds 500 more layers of bureaucracy that you have to get through. Sure.
So this thing is coming down, it's linked with iridium, and when you're going that fast and generating that much heat, you can't really get an optical connection. How is it connected with iridium to track its, and then the ionizing radiation would throw everything else into whack. How are you guys managing to do that?
So the way that they have configured that is essentially they're pointing, the point of using iridium and a lunar radio is that we're sending the signal back up. So instead of sending it down to Earth, that signal is not going through the plasma in front of the spacecraft, but it's going behind where there is less plasma and less interference. So that'll make its way back up to the iridium constellation, and then they send it back down to us.
One more question, William, were you going to ask a question?
Yeah. Are you going to test your spectrometer with a 15,000 Kelvin source?
So that is one thing that we're doing right now. It's actually a work in progress. We've seen, so from these spectra, we know that we have a predicted intensity. So spectral radiance, this is kind of the standard unit for intensity of light when we're looking at spectra. We have this predicted intensity, and there's actually a plasma lab on campus that has an intensity, a lamp that's calibrated with absolute intensity. So basically you turn it on and you know exactly how much it's emitting at, which apparently can go a lot stronger than this. So we'll be able to test the light and see how much it comes in. The survival of the cable, on the other hand, that's being investigated by the senior design group and building that thermal protection system around the cable so that it can survive. Thank you very much.
Thanks again.
Oh,
thank you everyone for hanging out here today with us. This